An algorithm is a sequence of steps which solves a problem when carried out in order. Today, we're going to discuss how a quantum algorithm can be understood as a similar set of steps. In order to accomplish this, we're going to need a language that lets us assemble the quantum operations we've seen so far into larger procedures. Such a language should have two properties. First, it should be easy to describe the effect of a small operation on a large system when we don't do anything to the rest of the system. Second, we should be able to easily write out a procedure that uses the output of one operation as the input for another. Of course, there's no reason to reinvent the wheel. We can look to classical logic gates for inspiration. Here we see two of the logic gates of classical computing, and an OR, each of which has its inputs and outputs carried by these wires. We can place an empty wire next to the OR gate to denote a bit which is passed directly through the circuit, and we can connect one of the output wires of the OR gate to the input of the AND gate, allowing us to build large, complicated logical circuits out of small, simple components. We can do something very similar with quantum operations. Here, we see the Hadamard operator, which has one input qubit and one output qubit. It's described by the 2x2 matrix on the right. There are also two qubit operations, such as the C0, which has two inputs and two outputs. This operation is described by the 4x4 matrix, also seen on the right. Now we come to the two techniques we use to compose small operations into large circuits. The first is that whenever there's an empty wire, we place the identity operator on it, and in order to calculate the total unitary that results from performing a small operation on a large set of wires, we take the tensor product of the operation with those identity operators. The second technique is for feeding the outputs of one stage of a circuit forward into a new stage, and it's perhaps a little simpler. We simply take the regular matrix product of the two matrices that describe the stages. It's important to be careful here, since the correct order for placing these matrices is the reverse of the order that they appear in the circuit. This is because in the matrix product, the rightmost matrix is the first one applied to the state psi. Before we use these concepts to analyze a quantum circuit, here are two more examples of two-qubit quantum operations which you may see later on, swap and CZ, which is also called C-phase. Swap can be used to exchange two states between two wires, which is useful if qubit states need to be moved from one place to another for some reason. The CZ, on the other hand, only places a minus sign on the 1-1 component of whatever state is input. Now that we've seen the CZ operation, let's take a look at how to analyze a quantum circuit which involves the CZ. Specifically, we're going to try to prove that we can generate a CZ using a C0 and some Hadamard gates on the target qubit that come before and after the C0. Now there are three ways to accomplish this, and we'll go through each of them. The first is the simplest, but also the most time-consuming. We're going to take tensor products of one qubit operations with identities on the empty wires, as seen here. Then, we can write out the entire circuit in matrix form. Multiplying these matrices one at a time gradually reduces the size of the problem. And once we've multiplied them all, we can see that the matrix describing the entire circuit is equal to the matrix describing the CZ that we saw earlier. A simpler technique, which works well on this circuit, is to calculate the effects on individual basis kets without writing them out in vector form. This saves us a little space. Here we can see that the effect of the Hadamard gate on the second qubit is to transform its state into the plus-minus basis. The C0 puts a minus sign on the 1- component of the state, since plus and minus are the plus and minus 1 eigenstates of the X operator, and the final Hadamard returns the states to the standard basis. This is identical to the action of the CZ gate on these basis states. The third and final method, which we'll use to analyze quantum circuits, is to express the relevant tensor products without using matrices, then try to simplify the resulting expression for the circuit. As we can see, the tensor product expression for C0, sandwiched with Hadamards, simplifies to 0,0 tensor h squared plus 1,1 tensor hxh. It's easy to show, using 2x2 matrix multiplication or ket notation, that h squared is the identity and that hxh is z, leaving us with a controlled Z operation, whose action we can verify using basis states. These three techniques, and the quantum circuits that they're used to analyze, each have a role to play in the design of new quantum protocols and are important tools for us to use to further our understanding of quantum algorithms.